In this class I'm going to look at the relationship between marginal and average cost, and we're going to look at the relationship between the marginal cost curve and the average cost curve to see how they link together, how they're related. I'm going to use a diagrammatic approach to this. If you're not happy with that, if you don't like diagrammatic reasoning, then just remember the relationships at the end. You won't be expected to prove the stuff that I'm doing here. Just remember the relationships at the end and that will be fine. But some of you will be curious, why is that relationship the way it is? And what I want to do is to clear that curiosity by running over it and showing where it comes from. Okay, let's start with the total cost curve. That's the total cost curve. That ultimately is based on the production relationships, and as output increases, what happens to inputs, or what happens to the relationship between inputs and outputs as output increases? Well, in many cases we have the law of diminishing returns that kicks in, which makes the relationship non-linear. It's not a straight line. As you double inputs, you don't double outputs. The law of diminishing returns might kick in. You might have to vary the number of workers per machine or whatever it is. So it's very seldom we'd get a straight line, if ever. And given that production lies behind costs, it's reasonable to assume that the total cost curve is going to be this sort of shape here. I've drawn it just like this one. I'm saying it starts off here. There's some fixed cost. So this one will be short run. There's some fixed costs here. That if we produce nothing, we still have the costs of the premises or the machines or the sunk cost or whatever it is. Then as output increases, costs will increase, but they start to fall off because, or they don't increase at the same rate, because workers are becoming more skilled at producing the output. They're more adept at production. Specialist machinery have been brought in, specialist departments. So average costs tend to fall off a little. And then as output continues to increase, the works become congested, people are tripping each other up, they're getting in each other's ways, production's getting more complex, costs are starting to rise, and eventually when we hit capacity, that's it, the total cost would simply be vertical. In other words, you can't increase output beyond this point. So that would be an intuitive or a very simple explanation as to why the curve is this particular shape. But we use this shape, generally speaking, to derive our average and marginal cost curves and show the relationship between the two of them. So let's work with this one and see where we get to. Okay, let's take a small change in output here. This one. That means we have a small change in costs. Now, a change in costs divided by a change in output will measure our marginal cost. So this vertical distance divided by the horizontal distance will show us our marginal cost. Okay. Not that simple. Let's say we explode this point to magnify it, to have a look at what's really happening in here. Well, this could be the magnified version. So here's our change in costs, delta C. Delta means change in cost, delta C, divided by delta Q, change in Q. So the vertical distance divided by the horizontal distance. The gradient of this line in here is our marginal cost. But you can see it's wrong. This is the true line up here. This is the one we've drawn. So you can see there is an error built into this one. So we've got it wrong. What we need to do really is to take delta Q to be very, very small. If we take it very small, what we'd do is we'd go up there, and you can see the gradient of that line would be less. It's still wrong. There's still an error. So we'd have to take it very, 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 very small down here, so that the error is negligible. And of course, those of you who have done calculus in the past will see what I'm playing at here. I'm reducing this measurable change in quantity down to something infinitesimal, something very, very small. So small we can't measure it, but it's just about there. So marginal cost is the change in the total cost divided by the change in quantity when the change in quantity is very small. Then we've got that relationship there is measured by the slope of the total cost curve. So really what we're after here is just the slope of the curve at a point, and the gradient of the slope. The gradient of the slope is the marginal cost. And that gets rid of this error we had earlier on, and it also gets rid of the complications of dealing with measurable output. So really we're talking here about the gradient at that point. Now, marginal cost is equal to the slope of the total cost curve. In theory, this is highly theoretical what we're doing, but in theory that's the relationship. So that's what it would look like. The marginal cost is tangential to the total cost at that point. So the slope of the tangent, the slope of this line, represents the marginal cost. Let's just think about what's happening here. Marginal cost down here would be, the slope would be very, very high. If it's just tangent there, then it's getting less. It's getting less. If you touch a point over here, you can see if you just draw the tangent at that point, it's just the slope of it is less than this one over here. As output increases, the slope is getting less. At some point it's at a minimum, after which it goes underneath. This is a point of inflection. After which it goes underneath, and we're picking up the tangents over here. And you can see the marginal cost is getting more and more until finally we reach capacity when the marginal cost would become astronomical. So there's a second tangent, and you can see the slope of this tangent is less than the first one, so marginal cost has fallen at the point A. Marginal cost is less here than it was earlier on. Let's put in the marginal and average cost curves and see what's happening here with those. Well, if we draw those underneath, like here, then what you see is the marginal cost here, the slope of this line, is the marginal cost. So if we were to take that down, we'd find marginal cost would be about there somewhere. So we're, by plotting out these slopes of the tangents, we're starting to trace out the marginal cost. At some points it becomes a minimum. Here's the minimum. It's after this it goes underneath and it starts to get bigger again. The tangent starts to have an increasing slope afterwards. If you draw it, just draw a tangent anywhere along here, you'll see that the slope is much greater than this one. This one has almost no slope here. And if we take that down, this Q point down, we'll find that's the minimum marginal cost, which is exactly what I've just said. That is the minimum marginal cost. It's the minimum gradient. Take it down, there you go. It's not equal to 0. If it was equal to 0, that would be touching the quantity axis. So it's just there. So that's the minimum gradient. And the minimum gradient is the minimum marginal cost. So we've linked total cost and marginal cost through our relationship here. Now let's look at the average. If I draw a line from the origin to the total cost curve a line from the origin to the total cost curve, which is just tangential to the total cost, it would be over here, this point. Now, if you remember how we work out an average, well, we just got the total, there's the total, divided by the quantity. There's the quantity, that's the total. So it's the vertical distance there divided by the horizontal distance. That's all you do to work out an average. But you can see the line I've drawn from the origin here is the minimum you can have. You can't get a line with a lesser gradient because it won't touch the curve. So that is the minimum gradient. In other words, that's the minimum average cost. There's the average cost, and that's the minimum point. So, just dotting it down, that's the minimum point. But if you look again at this one here, this average curve we've drawn, it's also a marginal. Our definition of a marginal is the line tangential to the total cost curve. It's the slope of the line tangential to the total cost curve. This one's tangential. It's tangential as well. The ones earlier down here were tangential. This one's tangential, although it's point of inflection. This one over here is tangential. So it must be that the marginal and the average are the same at this point. Both are just tangential. So the gradient of this line is also, the gradient of the line is the average cost and the marginal cost. But we know that the average cost is at a minimum. So there's the minimum average cost, just at that point there. And we know that marginal is the same. So the marginal cuts at that point. So the marginal cost curve cuts the average cost curve at its minimum point. That is incredibly important. So many students mix that up in exams and in projects and so on. So many students just draw the marginal cutting any old place. It can only cut at one point, the minimum average cost. It can't cut anywhere else. If you try drawing it anywhere else, arithmetically, not high mathematics, arithmetically, simple, straightforward arithmetic will tell you it can't be done. So please don't be sloppy about that. Get it right. The marginal cost cuts the average at the minimum point. And that's what this diagram tells us here. So we have the average cost, and it's the minimum average cost, and we've got average cost, AC, is equal to marginal cost. And there you go. So by using some of these diagrams, we've just simply traced across the relationship between marginal cost and average cost, and we end up with this diagram down here, which is typically the type of diagram we'll deal with in this type of economics, known as neoclassical economics. This is the type we'll use to analyze the firm. It'll turn up in competition. It turns up all over the place. So that's the relationship. It must be that the marginal cuts the average at its minimum point. And if you want to know why that's the case, I've just given it to you. If you're not happy with the diagrammatic explanation, just forget it if you want to, but remember this relationship, because this is important, this one here. But for some of you who are curious as to why this should be the case, and that's what good students should be curious, that's the explanation as to why it comes about. So I hope that was of some use. Okay, thanks for watching.